Okay, so we are recording now. Just so you've been legally, you've been informed. You are being recorded. If you ask a question at this point, your voice might get picked up by the mic, and just so nobody sues me. Okay, so here we are. We're going to start talking about vectors now. As you'll notice, I'm not necessarily going to go through and talk about every single sort of word in the entire book. So I'm going to kind of skip forward to the points that I think are worth discussing, no pun intended. So here I'm going to skip forward to this as a starting point. You'll see I have these things circled in yellow, and the idea is that's a reminder to me that this is something I want to talk about. This is how I do my lecture prep. So this should be a familiar picture to y'all. The XY axis, so some people like to think of it as. And this is a way of making an algebraic association to otherwise geometric things, right? So here's a point. That's a geometric thing. By having these axes, though, right, and a convention for how to use axes, namely you make this little rectangle here, like that, that allows you to associate an x coordinate and a y coordinate, and that which you can then combine to make an ordered pair, the coordinates of that point. So what I have highlighted in green here is a geometric thing. What I have highlighted in purple is what I'm going to call an algebraic thing. Right? And the connection between those is sort of the XY axes. Everybody on board? Old news, right? I mean, this is middle school, probably. I don't know, high school, middle school, somewhere like that. Okay, the reason I'm pointing that out is because we're going to take that idea and we're going to rip it off and we're going to apply it in a more complicated setting, namely in 3 dimensions, right? And here we go. So if you have a point in a 3-dimensional space, how do you describe that geometric point algebraically? And so it's with axes. So we, that axis, this axis, that axis. We now have, you'll notice, 3 axes. Often we'll use X, Y, and Z as the labels, but you can call them C1, C2, C3. Well, whatever, doesn't matter. And having done that, again, you make it's not a rectangle here. You're going to make a box, a rectangular box, you might call it. And that identifies then 3 coordinates, which you put together as an ordered triple. So X, Y, Z, something like that, is how you would describe algebraically a location in 3 space. Everybody cool with that? Okay. Now, here's an idea that freaks a lot of people out, and that is, what if you have not an ordered pair, which would describe a point in 2-dimensional space, or an ordered triple, which describes a point in 3-dimensional space? What if you have an ordered 4-tuple, right? X, Y, Z, W. What does that mean? Right? And it can be very intimidating. You might be thinking, it's the 4th dimension. Can you really do that? Is the 4th dimension time? How does this affect science fiction? There's lots of sort of, you can overthink this heavily. And really all it is, if I were to write down X, Y, Z, W, it's a list of 4 numbers. And I am personally not geometrically endowed with the ability to visualize what that looks like. But that's my personal limitation, right? I mean, there could still be a geometric, notion of 4 dimensions, and just because I personally can't think of it doesn't mean it's not a thing, right? So I like to point this out. There's nothing to be scared of if there is an ordered n-tuple with 4 numbers instead of 3. It's just, it's going to be harder to visualize geometrically. Look, 3 dimensions is harder to visualize than 2 dimensions. It's part of a pattern. There's nothing that creepy about it. Students will then very often suspect that, okay, well, yeah, but we're getting pretty far out at this point. We're talking about the fourth dimension, and come on, I'm an econ major. What is that? Do I really need to know about the fourth dimension? And why are we talking about, ordered n tuples with 4 coordinates? Well, there's a very simple answer to that question, which is not everything we do in math is strictly about describing points by their location in the physical world. That's just not all we do, right? Econ is actually a great example of where this is not the case. In econ, you draw all sorts of pictures. I have faint memories anyway from econ class of, like, y'all remember like PV PQ diagrams, I think they call them, price versus quantity, right? So the point is, you're talking about relationships between variables that aren't physical. Price is a function of quantity in different ways, and depending on your situation, right? But if supply goes down, price goes up, right? These are 2 quantities that relate, and which you would want to relate by writing equations and drawing pictures. Well, I hope it comes as no surprise. Sometimes there are more than 3 economic variables that are involved in an economic model, right? It is not at all rare to have 7 variables in an economic model, right? So now I cannot visualize 7 dimensions. Couldn't begin to. Not even close. Nothing even approaching that. So what? Right? That doesn't mean you can't write an ordered 7 tuple. P, Q, I, K, L, R, N. I don't know. There's probably an N in economics. So there you go. There's a list of 7 variables. So anyway, when we're talking about Rn, very often when we're talking about Rn, we're talking about R2 or R3, right? But not always. And in this class, we will focus mostly on R2 and R3 because I want to draw the connections between the algebra and the geometry. But don't make the mistake of thinking that we are only looking at R2 and R3. That's just for kind of geometric convenience. Many of the ideas that we're going to talk about in R2 and R3 generalize just fine in R7. So something to keep in mind. Okay, next thing I want to talk about, vectors. So let's talk about an example of, here's a physical quantity that we need to talk about sometime, and it's the idea of a displacement. Right? So let's think about this thing right here, this action of moving from this starting point to this ending point. And if you start there, stop there, you have performed an action of displacing in a certain direction by a certain distance or magnitude. Okay. All right. So this is a physical concept, the concept of displacement. Right. So what? How would I describe this physical concept of displacement? Well, I would need to find some way to communicate what direction the displacement is in, and I would need to find some way to communicate how far I'm supposed to go in that direction. Okay. Right. Importantly, notice that this concept of displacement makes perfect sense even if you don't know your starting point. So I could be lost out in the desert, right? And yet I could understand, not knowing at all about where I am, I could understand, okay, yeah, but walk northeast by 100 yards. That's a perfectly meaningful concept, even though I don't know where I am. Okay. All right. All right. Now here's a completely different physical concept. And that is velocity. Right? So if we're driving down the road in the car, we can talk about, our velocity. Velocity means, a combination of direction and speed. Right? And so, if that may be me right here. I'm here and I'm going, in a certain direction and, certain amount of speed that we'll call the magnitude of that velocity. Okay. And now this is a completely different physical quantity, right? Velocity is not the same as displacement. Displacement doesn't give any suggestion of any relationship with time. Displacement doesn't have anything to do with time at all. Right? Velocity does. So they're completely different physical things. But notice, both have a direction and a corresponding magnitude. The magnitudes play different physical roles. But both of these things have a direction and a magnitude. Okay. This is not a unique coincidence. There are lots of physical quantities, physical things that involve this pairing of a direction and a magnitude. It turns out that this pairing of a direction and a magnitude is crazy natural. So we give it a name. The pairing of a direction and a magnitude is called a vector. So that's what a vector is, in case you were curious. It's a combination of a vector and of a direction and a magnitude. Now, another example, by the way, forces. Forces are not the same as velocities. They're not the same as displacements. But forces, here, let's think about this pen here. Gravity is applying a force to this pen in a certain direction, right? And with a certain magnitude, namely how much does this thing weigh, right? There's more force on this remote control because it's heavier, and there's less force on this pen because it weighs less. Okay. All right, so a direction and a magnitude. All right. Okay, how do we represent vectors? Well, you've already seen me do it, and arrows are a great way to represent a direction and a magnitude because arrows point in directions that I can see based on how I draw them, right? They have magnitudes. Arrows have magnitudes in the form of how long did you draw that arrow. Yeah? Everybody on board? Okay. So here is a picture of an arrow representing a vector in R2. And here is a picture of an arrow representing a vector in R3. Okay. All right. Now, one thing to be careful about. You look at this picture here, and I'm going to ask a rhetorical question. How many vectors do you see there? And a lot of people would say, I see 4 vectors, and this is not true. This is one vector represented with 4 separate arrows that all describe the same vector. Because, keep in mind, now this is an important distinction, we use arrows to represent vectors, but vectors are not the same thing as arrows. Arrows are little pointy things with a little, with a shaft and a little seeming head on the end, and that you write with a pencil. That's what an arrow is. A vector, per the previous page, a vector is a direction and a magnitude. That's it. Vectors are not made up out of pencil lead. You ever see what I'm talking about? Right? So, let's look at these arrows. They're all pointing in the same direction. They all have the same magnitude. Forgive my artistic imperfections. Same direction, same magnitude, same vectors. Everybody on board with this? This is a big point. A lot of students get confused on this. This is one vector drawn with 4 separate arrows. Okay. Alrighty. Okay. So, there's a neat fact about how points and vectors relate to each other. Now, before we go into this, I want to remind you points we described with coordinates, right? Points are basically locations, right? Vectors, new concept, the combination of a direction and a magnitude. These are clearly not the same things, right? A vector has a direction. A point is just sitting there. Right? Okay. So, nevertheless, it turns out that there is a strong correspondence between points and vectors. And so here's how it works. If you have a point, the associated vector is represented by, well, vectors are of course represented by a bunch of different arrows, right? But one of the arrows representing the vector in question is the arrow that goes from the origin to the point in question. Right, so if you give me a point, notice that there is a unique arrow that goes from the origin to that point. Yeah? And now, yeah, okay, that arrow represents a vector. Lots of different arrows represent that same vector. This represents that same vector. That represents that same vector. There's all those purple vectors are pointing in the same direction. They're all got the same magnitude. Okay. All right. But the what we call the position vector, the vector, the way you get your hands on what is the corresponding vector given a point is by basing at the origin. Okay. All right. Everybody good on this correspondence? Any questions? By the way, I suppose there's nothing technically canonical about the origin being the starting point for the position vector. But it is what we're going to use in this course, and there's no reason to sort of pull on that thread. But anyway, it's an arbitrary but fixed choice for this course. Okay. All right. Now, I still want to emphasize that even though we have a one-to-one correspondence, I mean, you give me a point, there's a corresponding vector. By the way, let's turn it around. If you give me a vector that you represent by some arrow, right? If you say, hey, this vector, what's the corresponding point? Well, that vector is represented by lots of different arrows, one of which has its tail at the origin, and that arrow whose tail is at the origin, its head is the corresponding point. So for any point, there's a vector. For any vector, there's a point. It's a perfect pairing. Everybody's got a buddy. Perfect pair up of these things. I cannot emphasize enough, though, I'm not saying they're the same thing. Of course not. Points have locations. Vectors don't. Vectors have directions. They don't have locations. Right? Likewise, vectors have directions. Vectors have magnitudes. Points just sit there. They don't have either directions or magnitudes. So they're different things, but they do pair up in this canonical way. Okay. So with that in mind, we are going to blur the distinction between points and vectors because it's just so convenient. It's going to be really nice to talk about points by way of their position vectors, the vector that represents them, right? And it's going to be really convenient to talk about vectors by associating to them to their corresponding points. So, for example, let's look down at I guess I won't draw a picture, but let's look at I'll do it like this. So let's look at this point. Let's look at this vector. How would I describe that vector? And there's a temptation to say, okay, well, the vector is, we've got a direction, we've got a magnitude, we can talk about the direction by, let's measure the angle or something like that, and then we'll measure, how long is it, something like that. And you could do that, I suppose, but a really convenient thing to do is to say, look, this vector is associated to this point. That point has coordinates. And I can talk about this point by way of those coordinates. And so these coordinates are actually a pretty convenient way to talk about that vector. You see what I'm saying? Okay, so you're going to notice some seeming contradictions. I mean, the way I've got this written right here, let me go back to highlighter mode. I've got, what looks like a vector, P with a little arrow over, the little arrow means vector. this says I'm looking at a vector, but then I have equals, and then I have 1, 3. Well, that's a point. Right? Okay, well, yeah, but so here I'm using the blur. I'm blurring the distinction between them because it's just so convenient. Okay. All right. If you don't want to make that, some would call a slightly sloppy convenience, one thing you can do is use triangular braces. The triangular braces that you see here, the intention there is to make it explicit that we do not mean the point 1, 3. Triangular braces mean find that point, look at the vector associated to that point. That's what this vector P is. Right? So you can do that if you like. Some books do. Some books don't. This book does not. Most of the time. It's just in this context, there's the distinction is always, I think, clear as to, were you talking about the point or are you talking about the vector? Okay. All right. So by the way, here's another notation you'll see for vectors sometimes. So instead of representing coordinates as an ordered triple, A, B, C, written sort of horizontally, if you will, sometimes it is very convenient to write vertically. There's various good reasons for this. We're going to see a small motivation of this in a few minutes. We'll see a much stronger motivation later. Okay. A little bit of terminology. This is something you got to be careful about. I want to talk about this line right here, and let's talk about that vector right there. We've got this line L, we've got this vector V, and again, rhetorically, I ask, how would you describe in geometric language, how would you describe the relationship between V and L? And a lot of people would say, oh, V is in the line L. And the temptation to say V is in the line L is because, well, look at it. There it is. Tail right there in the line. The head right there in the line. The whole shaft right there in the line. Right? Very tempting to say V is in the line L. That doesn't really make any sense, though. Right? Let's talk about again. What is a vector? A vector is a direction and a magnitude. Vectors don't have locations. That vector isn't in the line. It's not in anything. It doesn't have a place. It's not in a location at all, as evidenced by the fact that that same vector is just as well represented by these other arrows. Right? Would you say that is in the line L? Certainly not. Not even close. Okay. All right. So the relationship that we're looking here, this vector V, let's keep all 4 of these arrows highlighted. This vector V, this line L, they have a relationship. I mean, there's clearly something, there's a connection between these things. Just don't say it in reference to the vector having a location, because that doesn't make any sense, right? What we would say is that this vector is parallel to the line. And this respects the fact that vectors have directions, not locations. Yeah? Everybody good? So, parallel, statement about directions. Lines have directions. Say that these are parallel, it just means they're pointing in the same direction. Cool, no problem. Okay. If you do want to talk about, what would it mean for a vector to be in a line, and again, technically it doesn't really quite make sense, but if you were to write, let's say, V is in the line L, how would you make sense out of this statement? And again, for the first thing you have to start with is, okay, vectors don't have locations. What do you mean it's in? So this is location talk. Doesn't really make sense, right? So you then have to interpret and say, oh, when you say V, you must be blurring. You must be referring to the point that V is associated with. When you say V is in the line, you mean the point associated with V is in the line. And that's what this picture looks like. Okay, you can see here we've got our vector V This is I drew it differently, of course, but there's our vector v. This vector v is associated to a point. What point is it associated to? Well, find the arrow with its tail at the origin. The point there is the head of the arrow whose tail is at the origin. So that must be the v that we're talking about that's inside of this line L. So this picture would be the interpretation of v is in L, not this picture. Everybody happy? Okay, let's talk about a little bit of algebra. I hope you all remember your Pythagorean formula. Let's see if I can get this on. There we go. So no big deal here, right? Y'all remember how to compute the length of the hypotenuse. So the length of that vector then, so the magnitude, which of course with magnitude is a distance as we draw arrows. That magnitude is the hypotenuse, and hypotenuses are computed with this formula involving that triangle. Yeah? Everybody good? Okay, so what about if you have a three-dimensional vector? This becomes a harder geometry problem. I'm going to leave this as an exercise for you all to do on your own. So suppose you have a vector like that, and just for visual convenience, let me drop a perpendicular. How would you relate this magnitude of that vector to the coordinates? Let's see, the coordinates would be like, that, and that. And notice this does not make a triangle. So how do you get your hands on the relationship between the green coordinates and the blue magnitude? It becomes a little geometry problem, and I'm going to point you in the right direction, which is to draw that little line segment like that. Now notice that you have two triangles. There's that triangle there, and there's this triangle here, right? And you can write down the Pythagorean formula for that yellow triangle. And of course, one of the edges is this thing here, which is another distance that it's not one of the coordinates. But you can write down the Pythagorean formula for that, hypotenuse of the leg of the yellow triangle, which is the hypotenuse of the orange triangle. Write down the orange triangle's Pythagorean formula and work the algebra around, and out comes this formula right here. Details for you guys. Please take the time to crank that out. Everybody good? All right. Okay. How do we, let's talk about adding vectors. What does it mean to add two vectors? I want to have a conversation about this before we write down the formula. A lot of y'all have probably seen this picture that, you take the formula is, and you take the one of the vectors and you put the tail of the second vector at the head of the first vector. How many of y'all have seen this little picture before? Quite a few. Great. Okay. I saw this at some point in, high school or something like that, and I remember thinking, okay, look, I'll do what I'm told, but I don't really get why. What an odd little convention to make, right? Why would we do this? And I think this is always worth exploring, right? Again, you don't want to view the learning of math as that you memorize your formulas, do as you're told, right? That's not what this should be. So when we make a definition, and this is a definition, by the way, when you make a definition, you should always think through, what is my motivation for making this definition? And there should be some motivation for making the definition. Sometimes it'll happen, and we're going to find this tomorrow, but sometimes it'll happen that the motivation is something that comes later. Right? We make the definition the following way because of how wonderfully everything's going to work out as a result. So sometimes I'll have to defer that, right? But as it turns out, we have a great answer to this question right here. So I'm going to ask again rhetorically, why would we make this the definition of what it means to add two vectors? And here's my point of view on it. Let's remind ourselves, what does a vector represent anyway? Vectors represent, well, like forces and velocities. But the very first thing that we wrote down, that vectors will help us represent, was a displacement. Right? So let's just ask the perfectly reasonable question of, if I were to be at some location, doesn't matter where, if I were to displace myself as indicated by this vector, and if after that I were to subsequently displace myself as indicated by that vector, grand total, you might say, right? How much have I displaced? And the answer is, when you start at this location, right? When you displace by, as indicated by that vector, that gets you to there. And having done that, if you then displace as indicated by that vector, that gets you to there. And grand total, again, you might say, you started here, you ended there. Grand total, you've displaced by that vector. So that is a really strong motivation, I think, for why you'd want to add vectors by way of this formula. Because this formula, or this picture, I'll say, this odd little head-to-tail story dovetails really, really nicely with one of the things that vectors are supposed to be representing, namely displacements. Okay. All right. So that's why we make that choice. It's not just arbitrary. Oh, by the way, good news. If you write down an algebraic formula for, how would you compute v plus w? There it is. Now, this formula is really appealing because, here, let me rewrite this formula. I'm going to rewrite this formula as V1W1 plus V2W2 is V1 plus V2 W1 plus W2. That's very appealing because, I don't know, it seems like just from a symbolic point of view, kind of, isn't this what we should? Don't we kind of have to make this the definition or something, right? It's tempting to say that, just strictly from a symbolic point of view, that this is what it should be. But this is absolutely not the case, right? We don't write down definitions of operations because they look good symbolically, right? We write down definitions based on motivations, intuitions. How does this relate to meaningful concepts? The formula is downstream from that. So it just happens to be in this wonderfully convenient coincidence that when you write down this very natural and meaningful motivation for what vector addition ought to be, you happen to get a convenient formula. Right? But that's a lucky break. It's not the motivation. Okay. By the way, notice while we're here, notice how nice it is. You'll see them. You can see it's kind of easier to motivate this formula by look at how that adds up to that, and that adds up to that, and it leaps off the page more conveniently because we wrote the vectors vertically. Right? Compare over here. It's a little harder to see what's going on. Yeah. Yeah. So V. Yeah, good question. Thank you. Let's see here. So I'll use blue. So V is O. Gosh, thank you. I'm sorry. You got me. Good catch. Sorry, I was in a hurry. I'm looking at the clock. I know it's almost lunchtime, and this is V2, and this is W1, and so, thank you. V1 plus W1, and this is V2 plus W2. Sorry, yeah, got ahead of myself. Thank you for that. Yeah. Okay, everybody see what I'm talking about? Okay, all right, let's see here now. Real quick, a couple of other quickie ideas. How do you multiply a vector times a scalar? What should this mean? Again, you can write down formulas, but that's not why you do things, right? Let's multiply. What should it mean to multiply a vector by a scalar? If that vector represented a displacement, multiplying by a scalar, well, keep walking, right? And just keep it. C times as far seems like a very reasonable definition. So this formula that the vector v. If you want to multiply the vector v times a scalar c, then just keep going in that same direction by a greater distance. Okay. Not hard to persuade yourself that the formula, where is it? Here, you get this formula. Okay, and since we are kind of out of time, I am going to do one last thing, and that is to talk about subtraction. What should it mean to subtract two vectors? And I'll point out two things. First of all, I'll zoom in here. What it means to subtract two vectors is kind of thrust upon us by previous choices, right? If you're going to subtract, you are adding a scalar multiple of that second vector. And we've already decided what it means to add vectors. We've already decided what it means to multiply a vector times a scalar. So we don't get to pick. Right? If we want algebra to have any meaning in what we're writing down, we don't get to pick what vector subtraction means. It's got to mean what it's got to mean. And then here's the second observation I'll make about it. I think a great way to make sense out of subtraction is from this formula, that the difference v minus w, well, it's the thing that when you add w gives you v. Right? I mean, again, it really better be. If it doesn't work out like this, then our algebra is unacceptably poor. Right? So notice that gives you a picture that's very satisfying. Here's the picture of subtraction. That is the vector that when you add to w, right, when you add these two things, you get v. So said differently then, the difference of v minus w is represented by an arrow that goes from the head of one to the head of the other when they're both in standard position. Okay. All right. So we're out of time. I will maybe say another couple of quick words about this section on tomorrow, but I do want to encourage y'all to go ahead and get started on the homework exercises this afternoon. I will update the syllabus right after lunch, right? So I want y'all to have something to work on, so do go ahead and start on section 1.2. We'll say a few more words about 1.2 tomorrow, and we're going to move on to 1.3. By the way, we are already behind schedule, but conveniently we have a lot of flexibility in the way the schedule's written, so we'll catch up. We'll be fine. Okay, see y'all at lunch.